Dr. Benny Karunakar sir is an associate professor at IIT Roorkee. Sir did his BTech in mechanical engineering from JNTU College of Engineering, Anantapur, AP. And then he did his MTech in manufacturing engineering from Indian Institute of Technology, Kharagpur. Sir has done his doctoral studies PhD, CAD-CAM in metal casting at Indian Institute of Technology, Kharagpur. Sir has memberships in Indian Institute of India Foundrymen and Indian Society for Technical Education. Sir has visited many countries: Japan, USA, Israel, Switzerland, UK, Germany, and other countries. So, Sir has published more than 24 national and international journals. So this is about little introduction about Sir. So now I would like to hand over this session to Dr. Benny Karunakar. Thank you, sir.
So a very good morning to every one of you, and I welcome you to this seminar talk. So actually, Dr. Srinivas Rao was, I think he has seen my web page in the IIT Roorkee website, and I think he was telling my biodata. Actually, that was the biodata, I think some 5-6 years back. So it was not updated. So actually, the publications are nearly 100 publications are there. My publications. Of course, I will be updating them very soon. And today's presentation topic is the developments and materials used for investment casting process, a review and modern perspective. Okay. Is my screen visible?
Yes, sir.
Okay. So this is the title of our presentation today: developments and materials. Is it fully screenable or partly visible? Screen.
Fully screen.
Developments and materials used for investment casting process, a review and a modern material perspective. Means in this presentation, we are going to see what is investment casting process and what are the developments that took place over the centuries, or in fact even over the ages, and what were the materials used for the investment casting process during the ancient times, and what are the materials used during the modern days, and what are its recent and latest applications. All these things we are going to see in this presentation. Okay. Now, history of investment casting. So I think all of you are aware of the process, investment casting process. So if I ask you what is the investment casting process, I think everyone knows. I think. Is there anyone who doesn't know investment casting process? So that I can start even at a lower level. Can I presume that everyone knows the process of investment casting? Okay, I think everyone knows. Okay, now history of investment casting process. What is the history? How long it has been there in existence? You see here, this has been in existence. This has been in use even in thousands of years during BC. So it is reported that this process was as old as 5,000 years BC, when the early man used this technique to produce the rudimentary tools. What are those rudimentary tools? See the spearheads. See nowadays, if a war erupts between two countries, so what is the weapon? Missile. Missiles. They use the missiles, and yes, they don't go to the borders. They sit in the military headquarters and they target the missile, and the missile will go and cause the destruction in the enemy's country. But olden days, what was the weapon? Spear. So this is the spearhead, you see, and to which a wooden handle was fixed, and they used to run for some time and they throw it on the other group, and someone will die in the other group. Now, the fact is, this spearhead is manufactured by the investment casting, even those days. How? See, initially they have made 3 spearheads, you see, made up of wax. So this is one spearhead, so this is one spearhead, and this is one spearhead. All those were joined together so that in one round, 3 spears can be manufactured. That was the concept. So all these were joined together, and there was a central tree. Now, sticking sand was compacted around this assembly of the wax patterns, you see, like this. After that, they have heated it. They have heated and they have made a small hole at the bottom. And what happens when they heat this mold? So this wax was melting and it has drained out. And now they are pouring the molten metal into the this cavity. So yes, it goes in and it fills this cavity. And once the cavity is full, yes, it raises. There is a raiser, you see, and yes, through this hole it raises, and they stop pouring. And after some time, and they have broken this sand, and they have taken the casting. So this is the solidified casting. Yes, they will be cutting this. They have to cut here, they have to cut here, and they have to cut here. And these are the finished castings of the spearheads. So this is how the ancient man has produced the spearheads during the ancient time, you see. So this process is as old as 5,000 years BC. Later, so the process that was used to manufacture rudimentary tools was later it was used to manufacture or to make art castings. For example, you see, this is an art casting, say made up of bronze. Most of the times we used to see bronze castings, you see. How they are made? Initially, they make a wax model. They make a wax model and yes, they put it inside a sand mold and they pour the molten bronze. That is a simple principle. Yes, these are all the art castings. Over the years, the investment casting was widely used for making art castings. So this is one art casting which is kept in the USA museum, you see. Now, even in India, so this process was very popular. So there was a popular casting called Dancing Girl, you see. So this Dancing Girl was made in India. When? It was made in India 2500 years BC in the Mohenjo-daro. Of course, this place is no more in India. It has gone to Pakistan. But India was not backward as far as this process is concerned. India was very much aware of this investment casting process. Later, you see the stages. Initially, the investment casting process was used to make rudimentary tools like spearheads, arrowheads, axe heads. Later, it was used to make the art castings. Later, it was used to make the dental crowns for the past century. In the year 1987, first time the dental crowns were made by investment casting process. You see, so the dental crown means the one the external feature that appears to us. That is the dental crown. You see, so this is the dental crown, and here you can see these are all the natural teeth, and this is the artificial tooth, and this is made by investment casting. Later, after the during the Second World War, you see, this process was used to make the turbine blades. You see, so this is the wax pattern, and this is the turbine blade. Now, the question is, yes, the ancient man has used this to make the rudimentary tools. Later, it was used to make the art castings. Later, it was used to make the dental crowns. Later, it was used to make the turbine blades. Why investment casting today? Today, why we should bother? There are several reasons why we should think of investment casting process. Why we should give importance to investment casting process? Several reasons. One is it can produce very thin and most complex features, as thin as 1 mm thickness, which may not be possible with other casting process. It offers excellent surface finish, 1.5 to 3.2 microns RA. It offers excellent dimensional accuracy. No or negligible finishing operations are required. Sometimes no machining, because surface finish is very good and dimensional accuracy is very good. Why machining? Just break that mold and take the casting. And it can be used to cast all metals and alloys. That is another important specialty of the investment casting process. Whereas if you take any other casting process or any other manufacturing process, all the metals and all the alloys cannot be processed. I will show you the details. For example, see, we are dealing with ductile iron, tool steel, stainless steel, aluminum, magnesium alloys, copper, bronze alloys, titanium alloys, and super alloys. Okay. Now these are all the different processes: die casting, forging, powder metallurgy, sand casting, welding, and investment casting process. You see, when it comes to the die casting, only aluminum, magnesium alloys, and copper, bronze alloys can be manufactured. Other materials cannot be manufactured. You see, when it comes to forging, tool steel, stainless steel, aluminum, magnesium, copper, bronze, titanium alloys, and super alloys can be processed. Ductile iron, no. Powder metallurgy, tool steel, stainless steel, aluminum, that's all, and titanium alloys. Only these four can be processed. Sand casting, almost all the alloys can be processed using sand casting except titanium alloys. And when it comes to welding, yes, steel, stainless steel, aluminum, magnesium, copper, bronze, titanium alloys, super alloys can be processed. What about tool steel and ductile iron? No, it is not possible. Now you see the specialty of the investment casting. When it comes to investment casting process, all alloys, all metals can be processed, can be manufactured. That is the unique specialty of the investment casting process. Any metal can be processed. Any alloy can be processed. Means any component of any metal, component of any alloy can be manufactured using investment casting process. So that is the greatest advantage of the investment casting process compared to other manufacturing process. Now, what are the applications of the investment casting process? Art castings and jewelry castings, that we have already seen. Even today, if we have to make art castings, see, we have to go for the investment casting process. And what about jewelry castings? Yes, sometimes we go to jewelry shop and we see big jewelry ornaments. So these are made by investment casting process. And both general and specialized engineering components can be manufactured using the investment casting process. Relatively simple levers to diesel turbochargers. Simple levers can be manufactured by investment casting process. And impellers, wheels, diesel turbochargers, these are the most complex components. Yes, they can be manufactured using investment casting. And extremely complex thin-walled electronic chassis components, medical hardware, including surgical implants, dental crowns, and many more complex components can be manufactured using investment casting process. Now you see, these are some of the applications of the investment casting process. The turbine blades, you see, the most complex features of the turbine blades can be accomplished using the investment casting process. Now you see, so these are all the pump and valve components. So these are manufactured by investment casting process. And here you can see hardware and lock components. Yes, these are manufactured by investment casting. Military and firearm castings. Yes, these are made up of carbon steels and these are manufactured by investment casting process. Now you see tool steel parts. Yes, so these parts are very familiar to us. We have seen these several times, but we rarely think how they are manufactured. These are manufactured by investment casting process. Now you see, what is this? So this is the milling cutter, phase milling cutter, you see, and it has several complex features. It is made up of, most of the times it is made up of high-speed steel or even latest tool materials. Means what is the specialty? They are very hard. So how to give the shape? Only by through investment casting process. Means initially a wax model will be made, means wax pattern will be made. Yes, around that ceramic mold will be created. Now this high-speed steel will be melted and it will be poured inside. And yes, after solidification is over, and we can break that mold and take the casting outside. Only thing is you have to sharpen it on a grinding machine. Yes, these are the Pelton wheel blades. Okay, so each blade is manufactured by investment casting. Now you see a revolver frame. So this is also manufactured by investment casting process. Yes, this is the duplex stainless steel corrosion resistant valve. Now you see aerospace components. These are manufactured by investment casting. Aluminum automotive components. These are manufactured by investment casting. So this is the copper casting, locomotive accessory. Investment casting of titanium alloys. So this is an emerging field. Nowadays, more focus is being given all over the world on to manufacture titanium alloy components. So these are used for in jet engines, okay, and also in the medical implants. You see, so these are the medical implants, surgical implants. So the specialty of the aluminum alloy is that it is accepted by the human body. That's the specialty. Recently, some work is being done on the magnesium alloys, but these are more well established that they are accepted by the human body. So surgical implants like hip joint, hip replacement joints, everything is manufactured by investment casting process, and the alloy used is the titanium alloy. Now investment casting of super alloys, you see, so this is the turbine impeller. You see, just imagine it's a complex features, the complex features of this impeller, very difficult to manufacture by using any other process. But through investment casting process, yes, this is possible. Now you see, jewelry items. So these jewelry ornaments items are manufactured by investment casting process. Now you see, so these are all the precision components, precision and tiny components, which is it is very difficult to manufacture these parts using any other process, but using investment casting process, yes, it is possible. Sometime back we have seen that small components as small as 1 mm thickness can be manufactured using investment casting. Yes, these are all such components, precision components. Now, so far we have seen the history of the investment casting process and the past applications and the present applications of the investment casting process. Okay. Now, what are the developments that took place during the 20th century? So there are mainly 4 developments: solid mold investment casting, plaster mold investment casting, mercast process, and the 4th one is the ceramic shell investment casting process. Of course, some of these have become outdated, but still it is worth to learn about all these processes. Now let us quickly review what are these 4 processes of the investment casting, and let us see what happened to these processes. First one is the solid mold or block mold investment casting. Okay. Yes. What is this all about? Initially in this process, ceramic slurry is made, you see. So this is the ceramic slurry. Now, this process is mainly used for making small components nowadays. Of course, we have seen the ancient man has done, the spearhead he has manufactured. So that time that was not a small component. It was a medium-sized component. Yes, even big components at that time they used to manufacture using this solid mold investment casting. But nowadays it is limited to manufacture small components. For example, you see these are the golden rings. Now the aim is to manufacture the golden rings. So these are all the wax patterns. You can just count. You see, nearly some, I think some 15 patterns are there. 15 wax patterns. You see, each pattern is meant for one ring. Now these are all assembled together, right? And these are all assembled together, and they are attached to a central tray. Fine. Now, after the assembly is over, this ceramic slurry will be taken and it will be poured inside. This slurry will be poured inside. The slurry goes around the wax patterns and it takes some time, maybe for a few hours, 5 hours or 6 hours. After that, it dries out. Okay, setting and drying. And after that, they will heat this assembly. So this is the ceramic vessel. So they will heat it and they will make a hole at the bottom. Then what will happen? Right. So this way, the wax assembly will be melting and it will drains out. Now inside, what is there? This shell is full of this ceramic slurry. Of course, now it is dried out, and inside there is a hollow cavity. Now they take the gold, they melt the gold, and they will pour it inside. And molten gold goes around, and it fills this gap, like this, and there it solidifies. And after solidification is over, yes, we get the solidified casting like this. Okay. Now, yes, they have to cut. They will cut at several places, and they separate the rings. So this is the principle of the solid block mold investment casting process. Now, what are the advantages of this process? One is the mold is strong because in the entire vessel we are filling the ceramic slurry. So the solid is strong and the process is simple. But what are the disadvantages? Poor permeability. What do you mean by permeability? Ability of the hot gases to pass through the mold and to escape to the atmosphere. Yes, during the pouring of the molten metal, yes, the molten material itself may carry certain hot gases, or it comes, it is poured into the mold and it comes in contact with the mold walls, and the mold walls react with the molten metal, and some hot gases are produced, and these hot gases have to escape through the mold wall. Somehow it has to escape and enter into the atmosphere. That property is known as the permeability. Yes, in every casting process, this permeability is very important. Even in the investment casting process, so this permeability is very important. Now, what happens to the permeability in this solid mold investment casting process? Throughout the shell, this ceramic slurry is filled, and this ceramic slurry is made up of fine ingredients, and the permeability is poor. Then what will happen? Sometimes hot gases cannot escape from the mold and they get accumulated around the surface of the casting, and a porosity forms, which is not desirable. Now, large consumption of ceramic slurry. You see, too much of ceramic slurry is to be used. So this ceramic slurry takes a lot of time for preparation, and after that, yes, you have to discard it. Now, another disadvantage is the longer setting time. Oh, it takes at least 5 to 6 hours. Sometimes it takes. It all depends upon several factors. It depends upon the environment. Of course, if it is a summer, yes, it may set in 5-6 hours. But if it is the winter or rainy season, it will take even more time. So longer setting time. So yes, that's why though the ancient man has used that time, this was the only process available in the investment casting process. Yes, the ancient man used this technique for making small components, medium-sized components, and also big components. But nowadays, this process is limited to for making small components. The next one is the plaster mold investment casting process. What is the principle? The principle is similar to the solid mold investment casting process. In the case of the solid mold investment casting process, what happens is we make a ceramic slurry made up of fine ingredients, okay, ceramic ingredients, that ceramic slurry will be poured inside the vessel in which there is a wax pattern. But instead, in this process, instead of the ceramic slurry, plaster of Paris resin is used. Plaster of Paris slurry. So this plaster of Paris slurry will be poured inside the vessel. That's the only difference. Now the question is why? Why this plaster of Paris resin or the slurry? Why not that ceramic slurry? The difference between the ceramic slurry and the plaster of Paris is that with the ceramic slurry, the surface roughness may not be very good. Surface finish may not be so smooth. After all, it is made up of ceramic ingredients. Whereas with plaster of Paris, we get very excellent surface finish. That's why people go for the plaster of Paris slurry. Okay, the plaster of Paris goes around this shell, and there it cures and means it sets. Again, it needs time, 5 to 6 hours time. And after that, yes, we have to heat it, and the wax melts and drains out. And after that, we have to pour the molten metal. After pouring, yes, after solidification is over, again we have to break this plaster, the solidified plaster, and the casting comes out. So that is another process, plaster mold investment casting process. Now, what are the yes, this is the solidified casting. You see, the process gives very good surface finish. As we have already seen. Okay. Now, what are the disadvantages? Used plaster cannot be reused. That is only for one-time use. So that is costly. Plaster of Paris is costly. Okay. And its cooling time is considerably longer. And it can be used only for non-ferrous alloys. What happens if we cast ferrous alloys? So this plaster of Paris contains some sulfur. And this sulfur reacts with iron in the ferrous alloys, and it forms ferrous sulfide, which is very detrimental. The third one is the Mircast process. What is this Mircast process? Now, what is the pattern material in the first two process? In the solid block of investment casting process and the plaster mold investment casting process, what is the pattern material? Pattern means the model which is used initially. What is the pattern material? Wax. Here, the wax is replaced by mercury. That's the one specialty. Remaining process is same. So this process, yes, solidified mercury is used as the pattern material. Yes, ceramic shell is made around the mercury pattern by repeatedly applying ceramic slurry and stucco. Okay, and after mercury is drained out, by raising its temperature, molten metal is poured into the shell. Now, what are the advantages? Advantage is that the pattern material is good, and it takes any shape we want. In the case of the wax, we have to melt it. For that, a furnace is required. Here, no furnace is required. Just at the room temperature, it is in the liquid state. So you give any shape and put it in the freezer, and it solidifies. Around now you take the solidified pattern. Around that you make a mold and bring it to the room temperature. The mercury goes out. Now you pour the molten metal. That is simple. But the drawback is mercury patterns are very heavy. The density is very high. Whereas with the case of the iron, what is the density of iron? 7.8 grams per cubic centimeter. Whereas with the mercury, the density is 13 grams per cc. Very heavy. Pattern production and shell building had to be done at temperatures below minus 39 degrees. Why? Only at minus 39 degrees, mercury will be fully freezing. If you do it in the room temperature, yes, it is in the liquid state. So if you want to make a pattern made up of mercury, you should work in an environment where the temperature is maintained around minus 39 degrees centigrade. Then only mercury will be in the solid state, and you can make a pattern. Around that, you can make a mold. So maintaining that much chill temperature is expensive. Now, the fourth one is the ceramic shell investment casting process. So this Mircast process is nowadays outdated because it's because of the limitations. The pattern is heavy and not only heavy, it is expensive. Mercury is expensive, and we have to maintain a very chill temperature for making the pattern and making the mold. So this process nowadays it is outdated. The fourth one is the ceramic shell investment casting process. So this is the fourth development. This is the fourth development. First one is the solid mold investment casting. Second one is the plaster mold investment casting. Third one is the mercast process, and fourth one is the ceramic shell investment casting process. What is this process? Here, wax is used as the pattern material instead of mercury, as in the case of the first two process. And ceramic slurry is made up of the following ingredients. You see, aluminum silicate powder, and so this is the powder. And we take colloidal silica. This is the binder. So aluminum silicate powder is 50%, colloidal silica 40%, water few drops, and fine silica sand 200 mesh 5%. Then we mix these ingredients for several hours. Then we get a ceramic slurry. Now these are the steps involved in the ceramic shell investment casting process. Initially, a pattern is made. Okay, so this is the these are the dies. You see, so when you close this die, inside there will be a hollow cavity. So this what is the shape of that hollow cavity? The shape of the hollow cavity is the shape of the component. Is similar to the shape of the component. So we inject the molten wax into this die. So for that we use a wax injector. So this wax injector will be melting the wax, and it will be injecting the wax into this die. And after some time, the molten wax will be solidifying, and the solidified wax die is coming out. You see. So now we want to make several castings in a single round. So now you see, in this figure you can see 8 such patterns are assembled together. You see, 8 patterns are assembled together, and there is a central tree, and there is a pouring cup. You see. Now this assembly after drying out will be dipped inside a ceramic slurry. Ceramic slurry again and repeatedly it will be dipped, and we will dip it, take it out. Some stucco will be sprinkled. Yeah, after that again you dip inside this ceramic slurry, take it out. Stucco will be sprinkled. Again dip it inside. Likewise, so repeatedly it will be dipped, taken outside. Stucco will be sprinkled. So likewise, at least 7-8 times. So this process will be repeated. Now a thick ceramic shell is created around the pattern. Right? This is the shell building stage. After that, wax melts at between 70 to 80 degrees centigrade. So wax will be melting and it comes out. Is my voice audible? Are you listening to me?
Yes, sir. Yes, sir.
Yes, sir, we are listening.
Okay. So this is the dewaxing stage. Next, after that, we pour the molten metal. After, sorry, this is the molten metal pouring. Here we pour, and after that, so we break this mold. You see here, we break the mold. After that, we cut and we separate the castings. So these are the 8 stages involved in the ceramic shell investment casting process. Now, are you able to differentiate this from the other process? In the case of the first process, the solid mold process, solid block mold process, where the ceramic slurry is filled in the entire vessel. Inside the vessel, we keep the pattern, and the entire vessel is filled with the slurry. Here, we are not doing that. Just we are constructing a ceramic shell around the pattern. What is the thickness of the shell? Maybe 8 millimeters or 10 millimeters. That's all. So this process will be utilizing optimum amount of ceramic slurry. It won't waste so much of ceramic slurry. Okay. Now you can see here. So we are if a turbine charger's rotor is to be manufactured. You see. So this is the wax pattern. This is the wax pattern. Now this wax pattern is repeatedly dipped inside the ceramic slurry and taken out. And you see, the ceramic shell is created like this. And to which we pour the molten metal. And after solidification, we break this shell and we get the turbocharger rotor like this. Yes, that is fitted here, you see, this one. Now, the question, the most important thing is, what are the challenges of this ceramic shell investment casting process? No doubt, nowadays, ceramic shell investment casting process is widely used. First one is used, the solid mold investment casting process, but nowadays its use is limited to the small castings. If you want to manufacture medium-sized components, people go for the plaster mold investment casting process. Now, you see, the fourth one, third one is outdated. The fourth one is the ceramic shell investment casting process. So this one is used for making medium and also large scale investment castings. Now, ceramic shell investment casting process has emerged as the most successful process among all the known process for the investment casting process. But still, this process too has certain challenges. What are the challenges of the ceramic shell investment casting process? One is the gas porosity and another one is the shell cracking. Gas porosity means gas bubbles will be forming on the surface of the casting. Shell cracking means the ceramic shell cracks during pouring or during solidification. So these two are considered as the main challenges. Now, what are the factors responsible for the gas porosity and shell cracking, and what are the preventive measures, or what are the investigations carried out by people around the world? We are going to see now. Now, this is the gas porosity. Yes, it looks like this. Why this problem arises? The first one is excessive ash content in the pattern wax. The fact is, the pattern wax contains certain ash content. Remember, we don't use a single wax. There are several waxes available. One is the paraffin wax, mountain wax, beeswax, okay, polycrystalline wax. Likewise, nearly 10 waxes are popularly used. What they do is they make a blend. Okay, see, each wax has certain characteristics. For example, paraffin wax gives fluidity, and mountain wax induces hardness. Each wax is known for certain characteristics. Now we take several waxes and make a blend so that we get the benefit of all these waxes. Now, in this process, it can so happen that one particular wax has higher ash content. Each wax has ash content, but it can so happen that when we choose different waxes to make a blend, it can happen that the ash content of the blend becomes more. Then what will happen? See, the ceramic shell has porosity, means tiny passages are there inside the ceramic shell. Okay, and when we pour the molten metal, the hot gases will be leaving from the ceramic shell. Now, because of this ash content in the pattern, during dewaxing stage, as the pattern drains out and goes down, this sulfur or this ash content sticks on to the ceramic shell, and it obstructs the narrow passages of the ceramic shell. You see, now you pour the molten metal. Actually, the shell has a tiny passages, but because of this ash content that is deposited in the surface of the ceramic shell, the hot gases cannot escape through the passages. So, excessive ash content in the pattern wax is responsible for gas porosity. Okay. Next one, poor permeability of the ceramic shell. Yes, the materials that you have used may be very fine, extremely fine materials you have used. Then what will happen? The narrow passages have disappeared after drying out. Then hot gases cannot escape through the ceramic shell. In such a case also, gas porosity will be forming. So these two are the main factors which are responsible for the gas porosity. Okay. Now let us see what are the investigations people have been doing to prevent this gas porosity in the ceramic shell investment casting process. Yes, prevention of gas porosity. One is using a wax blend that has minimum ash content. Means we have to conduct investigations, make a chemical analysis, okay, and see that the wax blend that you are using has minimum ash content. You cannot expect a wax blend to be free from ash content. That is not possible. Only thing is you see that it contains minimum ash content. And improving the permeability of the ceramic shell by mixing of special additives to the ceramic slurry. What are those special additives? Yes, so this was the work done by researchers in Korea. Actually, these were actually belonging to Korea, but they are currently working in a UK university. You see, the title of their paper is Investigation of the Fiber Modified Ceramic Molds for Investment Casting Process. So this was published in the Journal of European Ceramic Society in the year 2003. Now, what they have done is, so yes, we have to make the ceramic slurry, and in the ceramic slurry, they have mixed tiny nylon fibers. You see, so these are all the tiny nylon fibers. What is its diameter? The 600 microns. Diameter is 600 microns, and the length maybe 5 millimeters, 6 millimeters. So these fibers they have mixed into the ceramic slurry, and while these fibers are still mixed in the ceramic slurry, they have created a shell around the wax pattern. Now inside the the dried out ceramic shell, these nylon fibers were present. Now they have heated the ceramic shell, and they have, yes, it gained strength. And before pouring, what we do is we used to fire the ceramic shell. Why to fire the ceramic shell? There are two reasons. If second objective of additional strength to the ceramic shell. Yes, for that purpose we. I am seeing a message that the disconnectivity in the net. Are you listening to my lecture continuously? I think some disconnection. Are you? Is my voice audible?
Yes, sir. Audible.
Yes, sir.
Yes, sir, it is audible.
No, is there any discontinuity in between?
No, sir. Clear.
No, sir.
Oh, some message is coming to me that there is a poor connectivity like that. Okay, anyway.
Now I have muted all, sir. You please unmute and carry on. Sir, you are in mute mode, sir. Please unmute, sir. Yes, sir. Now we can speak, sir. Now we can speak.
Okay, is my voice audible?
Yes, sir. Yes, sir. Fine.
Okay. So now when the ceramic shell was fully dried out, so these nylon fibers were present inside the ceramic shell. So yes, we used to fire it, so to induce additional strength and also to remove the traces of the wax from the ceramic shell. Now that time these nylon fibers were burnt out. Okay, so when these tiny nylon fibers were burnt out, what happens? Okay, tiny passages were created inside this ceramic shell. Okay, so these tiny passages made a way for the escape of the hot gases. Yes, this has worked out. This was found to be successful. Okay, so they have incorporated nylon fibers to the ceramic slurry. Yes, here you can see. So these are the fibers. Okay, now inside the ceramic shell, yes, this is a tiny passes. You see, this is the tiny passes, and this is a tiny passes. So, see, they may look bigger, but you see the size. Size is very small. Maybe the diameter of this passes is maybe some 30 microns, less than 40. See, like this much is 40 microns. Means this is the diameter. Means diameter is maybe 13 microns, 30 microns. So tiny passages were created inside the ceramic shell. So this has helped the hot gases to escape from the shell. What are the drawbacks of these nylon fibers? Nylon fibers could be added only to the secondary slurry. The primary slurry was unmodified. What is this primary slurry and secondary slurry? Actually, when building the ceramic shell, we use two slurries. First slurry or the primary slurry, which is made of extremely fine ingredients. Extremely fine ingredients. So initially, the ceramic shell will be dipped inside the primary slurry once or twice. So a fine, thin layer is created around the wax pattern. So this coating is mainly meant for making fine surface finish around the surface of the pattern. Okay, and after that, our aim is not to create a very good surface finish to induce strength. So we use a somewhat secondary slurry, which is made of somewhat coarser ingredients. So two slurries are always used. Sometimes even three slurries: primary slurry, secondary slurry, and third stage slurry. Now, what happens is, so these nylon fibers could be added only to the secondary slurry, not to the primary slurry. If they add it to the primary slurry, the surface finish of the mold will be spoiled. Accordingly, even the surface finish of the casting will be spoiled. So they could not add these nylon fibers to the primary slurry. Only to the secondary slurry they have added. Now, what about the primary slurry? Of course, the thickness of the primary slurry is very small, maybe 1 millimeters. And after that, the second slurry will be given coating. Maybe the thickness of the primary slurry will be 1 mm. The thickness of the secondary slurry will be 7 mm or 8 mm. So in this 1 mm, that shell was equally impermeable as before. It was no permeability could be improved. Orientation of the fibers became a problem. So this works out provided the nylon fiber is embedded perpendicular to the surface of the pattern. Fine. If it is embedded perpendicular to the surface of the pattern, yes, tiny passes will be created and through which hot gas can escape. And if it is embedded parallel to the surface of the pattern, what's the use? That is not useful. So the orientation of the fibers became a problem. And addition of fibers at the corners became difficult. So these are the drawbacks of the nylon fibers addition. Later, some Chinese researchers have carried out different experiments. What they have done is, so the problem with nylon fibers is, main problem is, so embedding them perpendicular to the surface of the pattern is very difficult. They work only if they are embedded perpendicular to the surface of the pattern. Now, they have taken, these researchers have taken needle coke. Needle coke is a petroleum product. It's a carbonaceous product. Okay. Now, they have taken this needle coke. It looks like this. They have added 2% of needle coke to the ceramic slurry. Again, they have added this to the secondary slurry. Yes, with this needle coke present in the ceramic slurry, yes, they were dipping the pattern initially in the primary slurry, then in the secondary slurry, and they have made the ceramic shell. And yes, they have drained out the wax and they have fired this shell to induce the additional strength. During firing, what happened? So this needle coke got burnt out because it's a petroleum product. Okay, it got burnt out. So wherever there is needle coke inside the ceramic shell, it got burnt out and it made some pores inside the ceramic shell. So these pores were used by the hot gases to escape from the shell. So that is how the porosity problem has come down. Okay, so that was the work of these researchers. Now you see, so this is the microstructure of the ceramic shell, and here you can see tiny passages everywhere. You see, these are all the passages created due to the addition of the needle coke. Now, what are the drawbacks of the needle coke addition to the ceramic slurry? Again, the same problem, the problem that was faced with the nylon fibers. What's that problem? The needle coke could be added only to the secondary slurry. What about the primary slurry? They could not mix it to the primary slurry. What would have happened had they mixed this needle coke to the primary slurry? Tell me. Needle coke will be present in the primary slurry, means on the very surface of the mold. And during firing, that needle coke will be burnt out, and that inner surface of the shell will be spoiled, and that will not be useful. So needle coke could be added only to the secondary slurry. What about the portion where the portion which was constructed with the primary slurry, that was equally impermeable as it was before. The permeability of the primary slurry portion was not changed. It was not improved. Now, another topic is carbon diffusion into the cast component. What is this needle coke? It's a carbonaceous material. And during firing, what happens? Small amount of carbon will be still staying at the face of the ceramic shell. Now, during pouring, this carbon will be diffusing into the cast component, and it makes the component brittle. No, that is not desirable. Shell becomes extra brittle. You see, that's another drawback. Sometimes ceramic shell, if it is roughly handled, it breaks. Why? Because of the excessive brittleness. Okay. Now, reduction of gas porosity defect with addition of iodine and needle coke to ceramic slurry. So this is the work carried out in our laboratory at IIT Roorkee. So we have identified the challenges. Say people have added nylon fibers to the secondary slurry. The UK team and the Chinese team have added this needle coke after the nylon fibers. Both have added to this secondary slurry. What about the primary slurry? No modification could be done. The primary slurry portion of the ceramic shell was equally impermeable as it was before. So we came up with an idea, and we have filed even a patent for this. Now, yes, we have already seen. So in the ceramic shell, there will be two regions. The first region is the region created by the first primary slurry. Its thickness will be 1 millimeter. The secondary region will be made by the secondary slurry, and its thickness will be 7 to 8 millimeters. Now, in the first region, in the first layer, which is constructed with the primary slurry, to that we have added iodine. And to the second region, which is constructed by the secondary slurry, we have added needle coke. Now, our attempt is to improve the permeability of both the regions, primary region and also the secondary region. The fact is, iodine sublimes from solid state to gaseous state at about 546 degrees centigrade. We all know this. That is the unique property of iodine, sublimation. Means it is at the room temperature, it is in a solid state. And if you heat, any material will melt. And if you further heat, then it will evaporate. But when it comes to iodine, it is in the solid state. You melt, in the next minute it will become vapor. Now we have taken three proportions. You see, in one proportion is 0.25 weight, 0.25 weight by percent by weight, and another stage 0.5%, and another stage 0.75%, and needle coke 2% by weight, 2.5% by weight, and 3% by weight. So with these levels, we have conducted several experiments. Now these are all the experiments, different experiments combinations. You see, iodine was varied from 0.25, 0.5 to 0.75, and needle coke was varied between 0.2 to 0.5 and 2. Even 3. You see, totally 9 experiments were conducted. Now these are the parameters: stirrer speed 75 to 85 RPM, mixing time 24 to 30 liters, mixing capacity 8 liters, and working temperature, room temperature. And you see, and this is the ceramic shell we have created. You see, so these are the patterns. This is the ceramic shell. Now you see, FESM images of the iodine. Okay. Now this is the needle coke. Needle coke was looking like this in the FESM analysis. Now measurement of the flexural strength. You see these are all the different combinations. Here you can see iodine 0%, needle coke 0%. Means this is the conventional ceramic shell. And here you can see iodine 0.25%, needle coke 2%, iodine 0.25, needle coke 0.5, iodine 0.25, needle coke 3%, iodine 1%, right? Iodine 0.5%, needle coke 2%, iodine 0.5%, needle coke 2.5, iodine 0.5, needle coke 3, iodine 0.75, needle coke 2%, iodine 0.75, needle coke 2.5%, iodine 0.75, needle coke 3%. And so these are all the different samples. And when we measure the flexural strength, you see, the conventional shell has the lowest flexural strength, whereas the shell with iodine 0.25 and needle coke 2% has the highest flexural strength. You see, yes, this is one observation. Next one, we have even measured the tensile strength. Even with the tensile strength, the conventional has had the lowest tensile strength, whereas the shell with the iodine with 2.25% and needle coke 2% had highest tensile strength. You see the observation. Next one, inner surface roughness. Coming to the inner surface roughness is very important. Inner surface roughness of the ceramic shell. In that only we pour the molten metal. So if the inner surface roughness is very good, even the cast component will have very good surface roughness. Okay. So the inner surface roughness should be very fine. Now, when it comes to the inner surface roughness, the conventional shell means iodine 0, needle coke 0. That shell had the very good surface roughness, very good surface finish. You see, minimum surface roughness. Whereas it was maximum, you see, with the shells having 0.75 iodine and needle coke 2 and 2.5%. You see, with these shells it was highest. Whereas if you carefully examine the shell with 0.25 iodine and needle coke, it is slightly surface finish is slightly inferior compared to the conventional shell. Conventional shell is the best as far as surface finish is concerned, but the shell with iodine 0.25 and needle coke 2% is almost close to the conventional shell. And measurement of permeability. So we have even measured the permeability. That is the main objective. So our idea is when we add iodine to the primary slurry and when we add needle coke to the secondary slurry, permeability has to improve drastically. So we were measuring the permeability, you see. So for measuring the permeability, what we have done, we have taken this silica tube of 300 millimeters length. So this is the silica tube, right? And the ping pong ball. And we have attached this silica tube to a ping pong ball. And around this, we have given a shell coating, ceramic shell coating as usual. Initially, we have dipped this in the primary slurry. Then a layer is created of thickness 1 millimeter. Then we were dipping inside the secondary slurry repeatedly. Then take it out and put the stucco coat. And after we have dipped it 7 to 8 times, a shell is created around the pattern, around the silica tube, and also around the ping pong ball. Yes, this was dried up. Now this is the permeability testing machine. Okay, so this permeability testing machine, so this sample will be taken and there will be a tube, and that tube will be inserted here. Okay, so the here there is a, you can see air compressor. So air will be sent out at a high pressure, and the air will be entering into this tube, and it will be left like this, and it has to pass through the ping pong ball. So if the ping pong ball around which there is a ceramic shell, and if it has permeability, it will allow hot gases to escape or air to escape. If it doesn't have permeability, it doesn't allow air to escape. That is how we were measuring the permeability. If the more air is escaping, it has more permeability. Yes, this is the block diagram. You can see here. So this is the compressor. Okay, this is the regulator, and this is the flow meter, and this is another flow meter. Okay, and yes, this is the pressure gauge here. Now you see, so this is that ping pong ball, and it is coming here. So the air will be coming from the compressor and the regulator, and it will be flowing through these flow meters. So these flow meter F1 and F2 will give us how much quantity of air was passing through them. That is the purpose of these flow meters. Okay. Now air will be coming like this, and it will be passing through the test specimen ping pong ball, around which ceramic slurry shell is created. Okay, and then it goes out. Okay, and it will be this will be maintained at hot condition between 600 to 700 degrees centigrade. Okay, so that is the mechanism. Yes, we have measured the hot permeability. Now you see, the conventional shell had the lowest permeability. When it comes to the surface finish, it had the best surface finish, but when it comes to the permeability, it had the lowest permeability. And the shell with 0.75 iodine and needle coke 3%, it had the highest permeability. You see. Now, what we have to do? Do we have to go for the iodine 0.75 and needle coke 3? That is not the only thing required. That is permeability is not the only thing required. We have to see other things also. Surface finish. How is the surface finish? How is the strength? How is the flexural strength? How is the tensile strength? You see? Yes, this is the surface roughness. You see, surface roughness. The second specimen is better. You see, and when it comes to the tensile strength, the second specimen is better. So compare when we review all the properties, then we found that the second specimen seems to be a better choice. Means the ceramic shell, which is made up of iodine 0.25% and needle coke 2%, seems to be the better choice. It gives the optimum properties. Now you can see here. So this is the microstructure of the ceramic shell. You see, yes, because of the addition of the microstructure iodine, you see, small pores were created. You see, so this is the inner surface of the modified ceramic shell, and because of the addition of the needle coke, you see, pores are created. So these are the micropores. So these are the macropores. So this is again the conventional shell had no pores. You see, this is the conventional shell. Inside inner surface of the conventional shell, no pores. So this is the outer surface of the conventional shell, no pores. This is the inner surface of the modified ceramic shell with some iodine, 0.25 iodine. Yes, we can see small pores. So this is the outer surface of the modified ceramic shell with 2% needle coke. Yes, macropores are there. So yes, with 0.25 iodine, these are the images you can see, and with 0.75 iodine, yes, More pores are there, but with 0.575 iodine, what is happening? Other properties are diminishing, like surface roughness is not acceptable. So considering all those factors, so this 0.25 addition seems to be better. That is what we have filed in the patent. Now these are the conclusions based on the iodine and needle coke modification. Modified ceramic shells with the addition of iodine and needle coke exhibited improved permeability. And as compared to the conventional shell, modified ceramic shell possess higher flexural and tensile strength. The flexural and tensile strength of the modified ceramic shell started to decrease as the amount of iodine and needle coke were increased beyond an optimum level due to increased number of pore formation. That is what we have seen. As we increase the iodine content, no doubt permeability will be increasing, but the flexural strength and tensile strength is decreasing. Why? The iodine, as iodine is increasing, the pores will be increasing. As the pores will be increasing, the strength will be decreasing. Simple. And all the modified ceramic shells exhibited slightly poor inner surface finish as compared to the conventional ceramic shell. As far as the surface finish is concerned, conventional shell is the best. But if we want to improve the permeability, yes, we have to compromise. And iodine modified ceramic shell with 0.25 iodine is a better choice. So the optimum amounts of iodine and needle coke addition to the inner and outer ceramic slurries to obtain the optimum ceramic properties were found to be 0.25 iodine and 2% needle coke. Okay. Now, what are the other challenges? So far, we have seen the first challenge, gas porosity. Right? So gas porosity is the challenge. So we have seen what others have done. People have added nylon fibers. People have added needle coke to the secondary slurry. And in our IT Roorkee lab, we have added iodine to the primary slurry and needle coke to the secondary slurry. And that work was successful. So that is the problem as far as the gas porosity is concerned. What about the shell cracking? What are the investigations carried out around the world to reduce this shell cracking? First of all, factors responsible for shell cracking. First one is abrupt expansion of wax pattern. What is the pattern material, if I ask you? Wax. That word is not correct, not wax. It's a blend of waxes. Several waxes we take and we mix in different proportions so that different properties can be balanced. Fluidity, hardness, right? Minimum expansion, all these can be balanced. Now, around the wax pattern, we create a ceramic shell. We build a ceramic shell. After the shell is created, after the shell is dried out, we have to take the pattern, wax pattern outside. Okay, for that what we do? We take the this ceramic shell in which wax is present and we put it inside a oven. And slowly we raise the temperature. And what happens? The wax will be melting and it comes out. That is what is expected. But another thing can happen. What can happen? Before it melts and comes out, it can expand. Don't you think? The wax present inside the ceramic shell can expand before it melts. If it starts expanding, its rate of expansion is more. Its coefficient of expansion is more compared to the coefficient of expansion of the ceramic shell. Then what happens? It exerts tremendous pressure on the walls of the ceramic shell. Then what happens? The ceramic shell cracks. Why it is happening? Because of the abrupt expansion of the wax pattern. The entire labor that you have put to create this slurry, to create the ceramic shell, everything is lost. Why? Due to the abrupt expansion of the wax pattern. Another reason, another factor responsible for the ceramic shell cracking is poor mechanical properties of the ceramic shell. Means the ingredients that we are using may not possess good mechanical properties. In such a case also, even though the wax may not expand abruptly, so at such times the shell may crack. So these are the two factors responsible for the shell cracking. Now let us see how to handle this. Now people are using ice patterns for making investment casting. What are the, if I ask you what is the pattern material in the investment casting, you all will agree that it is the wax. Of course, people have used the mercury, which is now outdated. Now recently, people are started using ice patterns. You see, so this is the ice pattern. You can see here, this is the ice pattern, and around the ice pattern, so they are making the ceramic shell. After all, water freezes at 0 degrees centigrade. It doesn't require so much chill temperature as in the case of the mercury pattern. Mercury pattern required minus 39 degrees centigrade to construct ceramic shell around that. Whereas if we can maintain 0 degrees or little less than 0 degrees, maybe -5 or even -10, would be good enough to work around the ice pattern. So they have made ceramic shell around the ice pattern. And while the shell is created, now slowly they have brought it to the room temperature. Then what will happen? Tell me. When this ice pattern around which a ceramic shell is created is brought to the room temperature, what will happen? Ice will be slowly melting. Is it not? Maybe it is at 0 degrees. When they bring it to the outside, it is at 0 degrees. Slowly, its temperature will be increasing. Then it will be coming out of the ceramic shell. As it is melting, what happens to the ceramic shell? Do you think that pattern will expand and break the ceramic shell? As previously it occurred? You try to heat the ceramic shell in which there is ice pattern. Heat that ceramic shell in which inside there is ice pattern. Will it expand? We all know the abnormal expansion of water. What happens? When you cool down water from 4 degrees to 0 degrees, instead of contracting, it will be expanding. That is how we call it as the abnormal expansion of water. Why? Same is the case in the vice versa also. Means when you increase the temperature from 0 degrees to 4 degrees centigrade, so instead of expanding, it will be contracting. That is the nature of the water. So absolutely there is no expansion of the pattern. So no chance of breaking of the ceramic shell due to the expansion of the pattern. Yes, the pattern comes out very successfully, and yes, after the pattern is removed, means after the water is removed, yes, you can pour the molten metal, and this is the cast component. So this research was done in the year 2002 by a USA team. So this paper was published, and more countries are adopting this technique. One thing is they need a chill temperature. They have to work. They need a working environment, maybe -5 degrees centigrade. That is good enough. Now these are the ice patterns, done by other investigators. Now enhancing the strength of the ceramic shell with addition of glass fibers to the ceramic slurry. So another project we have done, that is the keeping the strength of the ceramic shell in consideration. We have done one project to improve the permeability of the ceramic shell. That was over. So this is another project to improve the strength of the ceramic shell. Okay, what we have done is addition of the glass fibers to the ceramic slurry. Yes, most glass fibers are silica based, you see. So 50 to 60% it contains silicon dioxide and contains a host of other oxides of calcium, boron, sodium, aluminum, iron, and so on. So they look like this, glass fibers, tiny fibers. The length will be 5 to 6 millimeters. And what is the thickness? Thickness will be in few microns. So these are the glass. So these fibers were mixed to the secondary slurry, not to the primary slurry. Yes, yes. In the case of the conventional slurry, so these are the ingredients. You see. So this is the binder. Okay, And in the modified slurry, yes, we have used the additive, you see, nylon glass fibers, you see, 0.1 to 0.7% by weight. GF means glass fibers, you see. Yes, we have constructed the ceramic shells. So this is the conventional shell, you see. There is a crack, you see. There is a crack at the corner. Why? Maybe due to the expansion of wax, or maybe sometimes expansion of the wax may not be there. Due to sharp edge, there was a crack, you see. But we have made modified ceramic shell in which glass fibers were mixed. No crack, you see. So these are the shells created, made up of ceramic slurry with the glass fibers. Now, yes, these are the FEM images of the glass fibers. Yes, they look like this. Yes, this is the EDX analysis. Now you see the result. Okay, you see there are totally 5 experiments. In the first experiment, glass fiber addition is 0, means this is the conventional shell without any modification. And here we have added 1% glass fiber. Here we have glass fiber is 0.3%, glass fiber is 0.5%, and glass fiber is 0.7%. Okay, and we have evaluated the permeability. The conventional shell had the highest permeability, whereas as we keep increasing the glass fiber addition, the permeability was gradually coming down. Next one, flexural strength. See, in the 5 experiments, the conventional shell had the lowest flexural strength. And you see, and as we were increasing the glass fiber, the flexural strength was increasing up to 5%. And as we increase beyond 5%, or sorry, 0.5%, and it was coming down. Next one is the tensile strength. Coming to the tensile strength, the conventional shell had the lowest tensile strength. And as we were increasing the addition of glass fiber, the tensile strength was increasing up to 0.5%, and then it decreased. When it comes to the surface roughness, when it is almost no change. In all the experiments, the surface roughness was same, surface finish was same. Why? Because we have added glass fibers to the secondary slurry. We could not add, or we should not add to the primary slurry. Why? They will spoil the surface of the shell, inner surface of the shell. So we cannot add these glass fibers to the primary slurry. So it doesn't matter. Now you see here, so FESM images of the glass fiber modified shells. Glass fiber modified shells with 0.1%. This is with 0.1%, and this is with 0.3%. This is with 0.5%, and this is with 0.74%. You see. Now at 0.7%, it found bundling and cluster. It was not good. Okay. Whereas 0.3%, 0.1%, 0.3%, and 0.5%, so they are acceptable. Now, these are the conclusions based on the glass fiber addition to the ceramic slurry or the secondary slurry. Modified ceramic shell possessed lower permeability. Permeability is reduced because after firing, the glass fibers act as obstacles for the hot gases to escape. As in the case of the nylon fibers, they cannot be fired. So they were burnt. Nylon fibers were burnt. So these could not be burnt. So they remained as obstacles for the passage of the hot gases. So that's how the permeability has come down. Next one, modified ceramic shell showed higher flexural strength, tensile strength, as the glass fibers form a strong bond to the matrix, creating obstacles to the crack growth and contribute to load bearing. Yes, as we increase the glass fiber addition up to 5%, what happened? The flexural strength got increased, tensile strength was increased, and they were creating the obstacle to the crack growth. And as the amount of glass fiber addition increase beyond 5%, 0.5%, the strength of the shell decreases. Hence, the optimum amount of glass fiber to the addition should be 0.5%. So this is our conclusion. Okay. Thank you. So I hope this presentation was useful. So I thank the organizers for inviting me to deliver this talk. So if you have any doubts, you can interact with me for a few minutes. Any doubt? Any clarifications?
Yeah, participants are requested to raise your queries either through chat box or you can ask directly answers to. Thank you all for joining, and thank you, sir, for your valuable time that you have spared with us to give informative and knowledgeable session on these novel materials in investment casting. Thank you, sir, very much for giving us a great lecture to us. Thank you, sir, once again, and thank you all for joining. We will start the third session of our today's FDP at 3 o'clock. We will be starting at 3 o'clock. So if you have any other doubts, you can post through chat box, and sir will be answering through various more. You can directly contact sir also through IIT web page. Thank you all once again for joining. So with this, we are ending the second session, and we will come back at 3 o'clock. The link will be the same, and hope we will all join in that session also. Thank you. Thank you, sir.